When you turn on a tap just a fraction, the water often forms a perfectly smooth, glassy cylinder. In this state, every drop follows the exact path of the one before it, creating a sense of frozen motion. But open that valve completely, and that order shatters. The flow becomes a thrashing, unpredictable mess that seems to have no internal logic. While it looks like total chaos to the naked eye, fluid motion at lower speeds is actually governed by an incredibly disciplined set of rules. To find the order within this movement, physicists zoom in to map the microscopic, invisible trajectory of individual fluid particles. This mapped path is called a streamline. It acts as a permanent record of exactly where a single particle travels as it flows through the system. This diagram shows a single streamline. Drawing a tangent line at any point identifies the precise direction of the fluid's velocity. In a steady flow, these paths follow a rigid geometric law. Two separate streamlines can never cross each other. This is a matter of definition. In a steady flow, the velocity at any fixed point in space remains constant over time. If two streamlines crossed at a single point, a particle arriving there would have two different velocities at the same time, a geometric contradiction that would instantly break the steadiness of the flow. Because these paths are locked in place and never intersect, they form a stable, permanent architectural map of how the entire fluid moves. When we observe thousands of these lines moving together, they form a tube of flow. If the pipe narrows, the streamlines must adapt. Since they cannot cross, the entire bundle is forced to crowd together, squeezing through that narrow center. This creates a physical constraint based on the conservation of mass. The total fluid entering the pipe every second must exactly equal the amount exiting it. Because liquids like water cannot be compressed into a smaller volume to fit the space, the fluid must use a different physical mechanism to move that mass through the bottleneck. We can calculate this movement by looking at the variables that define the flowing mass: the fluid's density, the cross-sectional area of the pipe, the velocity of the flow, and the time interval. The mass passing point P equals the mass passing point R. Density is constant for incompressible fluids, and time is continuous, so they cancel out. What remains is the equation of continuity. Area times velocity always remains constant. This formula is a direct mathematical expression of mass conservation. It describes how a fluid must behave when its path is restricted. In practical terms, this means that to keep the flow rate constant, whenever the pipe's area shrinks, the velocity of the fluid must proportionally increase. This is why water shoots out faster when you constrict the opening of a garden hose with your thumb. By reducing the area, you force the velocity to spike. This diagram illustrates a visual rule for fluid dynamics. Closely packed streamlines always identify a region of high-speed motion. In contrast, when the streamlines are spaced far apart in the wider sections of the pipe, the fluid is moving much more slowly. By learning to read these maps, we can predict the speed of a fluid simply by looking at the density of its streamlines. Let's return to the transition in our pipe model. At the exact moment the fluid enters the narrow bottleneck, it is forced to speed up. In physics, any change in an object's velocity is defined as acceleration. Newton's laws tell us that an object cannot accelerate on its own. A net physical force must be acting upon the fluid to cause that change in speed. If the pipe is horizontal and gravity isn't a factor, what is actually pushing the fluid from behind to make it shoot through the bottleneck? That force is created by a difference in internal pressure between the wide and narrow sections. This pressure gradient provides the mechanical push that drives the acceleration, a relationship that serves as the core mechanism behind